So this is an explanation on how to use your microscope to estimate the size of objects like cells and other structures when you don't have a lens micrometer, but you do have a simple clear plastic ruler. And this is an image showing the practice document that I have for you guys. So make sure you work on that document after viewing this. So let's start with a simple analogy here. Let's say we have a plate, and this plate here is going to be an analogy to what you see under the microscope. When you're looking under the microscope, the field that you look at or what you're able to see looks round in structure. So here we have a round plate for our analogy. And let's say that this plate is about 12 inches, which is approximately 30 centimeters in diameter all the way across. And let's say we put some fruit on there. Let's say that we have some large apples or some kind of a fruit on there. And when I put them on the plate, they're not all the exact same size. But what I do see is that roughly 3 fit all the way across the plate. And so if I know that that plate is 12 inches or 30 centimeters, you can actually use that information to estimate the size pretty quickly, because if about 3 fit all the way across the plate, then it's almost intuitive to say, let me just take the diameter and divide by the number of apples that go all the way across, and that would give me an estimate of the size of one of the apples, at least the average size for them. So what are we actually doing there? In concept, you're taking the diameter of the plate and you're dividing by the number of apples that you see fitting all the way across there. So n number is the fit number, the number that fit all the way across. And so if we do that, we would take your 30 centimeters and you divide by the 3, and that gives you approximately 10 centimeters for each of those objects that are on the plate. If we did inches, then it would be 12 inches divided by 3, so that would be about 4 inches in diameter. So we have now just developed a concept equation for estimating size if you visually. As long as you know the diameter of the plate or the field of view of the microscope, then it's basically the diameter. And in the microscope, we're going to call that the field of view, how much you can see, and divide that by your fit size, which is the number of objects you see going all the way across. So this is an important equation that comes up on the document. Now, to use another example here of what actually happens in the microscope, the problem with the microscope that we're going to have is that the size of the plate changes, right? It's like if I'm going to zoom in, then I'm going to see less and less of the plate. So the circle changes in diameter. So here's an example here. What I did was I took an image through a tube, a cardboard tube, like the kind that they wrap toilet paper comes in. And so I put that tube up to my face, and I put my phone right behind the tube and took a picture of the wall there. And when I did that, this is what I saw there. And if I know the diameter of that tube there, then I can probably use that information to estimate the size of this of the picture on there. And so I actually did that, and I put a measuring tape on there, and we got 80. When you actually zoom in to the image there, you can actually see the writing on there. And on the original image, I can actually tell that started at 9 centimeters. This is 81 centimeters. And so when I do that and you subtract the 81 centimeters from 9, because you don't start at 0, you get 72 centimeters, and that's the actual distance all the way across. And so that's my diameter. That would be my field of view. So now when I go back from that same distance, this shows that the diameter of your field of view was 72 centimeters. The field of view is what you can see. It's like the same shape as the plate here. And then here's my image right here. And so now I can't put a bunch of apples on a plate, but I have an image of an object in there, in this case the picture, and I can try to visually estimate the fit size. So I can say, well, the picture actually happens to be lined up right at the edge or near the edge. So say, well, that's one picture. So visually I can estimate. If I put another one and lined it up right by there, that other one would come to about right there. Okay? And so that would be my second picture. So that's 2 pictures. And then the next one would actually go off the field of view. Okay? And so when I do that, it might be somewhere about right there. So you're visually estimating this. And so when I do that, this is 0. This would be 1 object. That's the second of the same kind of object. And then my diameter ends right here. So we don't go a full 3. We go almost halfway into that one. So that makes here, I would say that now is it's not 2 and it's not 3, but maybe it's 2.4. So my fit number here would be about 2.4. And I know the diameter because it was measured earlier. So my field of view is 72 centimeters. And if we go back to that concept equation, which was the size is equal to the field of view divided by the fit number, then you just plug in the numbers, 72 centimeters, and then you divide by the number you estimate to go all the way across. And when you do that, the calculation comes out to about 30 centimeters. And this is just by looking at the diameter, the field of view, and then visually estimating the fit number. I actually went and measured the picture later after doing this estimation, and it was a pretty good estimate. The length of the picture frame was actually about it's like 30.31 centimeters, about 30.5 centimeters. So the technique works quite well in this case. Now, the key to doing this, when you're looking at things under the microscope, because when you look at things under the microscope, they're going to look like this, except very small, and you can't go and measure them with a ruler when you're looking under the microscope. So what do you need to do? You need to know the diameter of the field of view. But the thing is, when you change magnifications, you start off at low magnification, and then you go to higher magnifications, you're actually seeing less and less of the specimen you're looking at, or the field gets smaller, in other words. And the analogy that plays out here is if I start to walk closer to the picture, like we did up here. So if we start to walk closer and closer to the picture, the image is going to look bigger, but you're going to see less and less of the wall, right? So your field of view gets smaller. So I took some pictures moving closer, and so this is moving from 5 feet away, which was the initial picture was taken, and now I'm at 2 feet. And so this is the original diameter. That's your diameter was 72 centimeters, but the diameter of the field now is smaller. So this is your original field of view, and this is the new field of view, and it's no longer 72 centimeters. It's something smaller, the new field of view. And then I actually moved to a half a foot away, and this is, again, the original diameter is still 72 centimeters, but this field of view, the new one, is even smaller. It's much less smaller. It turns out there's a relationship between how close you are, or in other words, how much you've magnified or zoomed in, and the diameter of the field of view when you compare it to your field of view of the original one. And so we're going to be doing that, or looking at that. So here's your microscope. You want to make sure you view the parts of the microscope here. And your parts of the microscope here, your ocular lenses there, they usually magnify magnification of 10, and then here's your objective lenses. Your objective lenses magnify the object, and then the oculars magnify the image there, and then both are combined to make your full image. You always start off with your small lens, smallest lens, the scanning lens. Then you move to the low powered, and then the high powered, and then if you need to, you can go to oil, which requires special techniques. To get your total magnification, you're going to multiply your ocular lens times your objective lens. And so the objective is always going to be 10 power. Your scanning is 4 power on most microscopes, so it's 4 times 10 would give you a total magnification of 40. The low-powered objective is usually 10, so 10 times the 10 would give you a magnification of 100, and then the high power has a magnification of 40 times the oculars gives you total magnification of 400, and then your oil lens is 100, has a power of 100, and then you multiply that by 10, and that gives you a total magnification of 1000. So the general idea here is you either prepare a slide or you have a store-bought slide that you see there. that's been prepared by a science supplier. And you're going to put that slide on the stage. And when you put that slide on the stage, depending on what it is that was the specimen was on there, you would see that whatever it is in your image. And this is under scanning power, so the total magnification is 40. Now, if I move up to low power, I'm going to see less of the specimen. My field of view has gotten smaller. So here under low power, you see this the magnification is a total power of 100. And so this brings up the idea here that you should know that when your magnification is going to increase, what happens to your field of view, the diameter that you see, that decreases. So the two variables move in opposite directions. That's saying they're inversely related. When one goes up, the other one goes down. And so basically the idea is this. You are going to be asked to look at some images, and then based on knowing how big the field of view is, you can estimate the size of these structures here. For example, a question might ask you to estimate the size of the ovule, or in this case the embryo sac here. And that in cases where you're being asked to do a question like this, you're going to learn what the embryo sac is later when it comes to the plant structures in the flower. But in a case where I'm asking you to do an estimation of size, I'll give you guidance. So just like I'm doing right now. So this structure would be your embryo sac, and then I might ask the size of the integument cells. Those are the cells that surround the embryo sac. So that's there. Now, in order to do this, you would need to know what the diameter of the field of view is, just like we knew the diameter of the plate earlier. So what are the two things you're going to need? In this technique, you're going to need to know the field of view, and you're going to need to know your fit numbers, right? So you would have to, in this case, to be able to do this, you need to know what the field of view is under high powered, which is 400. And if you're trying to do the embryo sac, you need to visually estimate what the fit size is there. You also need to do that for the integument cells. For this large structure, the embryo sac, I think if I were to line it up on the edge here and then estimate, it's going to be maybe one full one and then part of another one. So it'd be like maybe 1.4 or 1.5 or something like that. And then for the integument cells, pretty easy. All you have to do is count the number of cells as they go all the way across there, because they're actually lining up end to end going there. And that could give you your fit size for those. But basically that's what you're going to need. So the general technique is this. You would use a ruler, since we don't have a lens micrometer. You want to make sure you use the metric side here, not the inches side. And the metric sides of a ruler is usually divided into centimeters or hundredths of a meter. And then the little marks are the millimeters. And when you're looking under the microscope, even under scanning power, you're only going to be able to see a handful of millimeter marks. So we're actually only going to be able to focus in and zoom in to that level there. So if I were to put this ruler here and put it on the stage under those lenses, turn on the light, and then look at the image under scanning, this is what it would look like here. So this is actually, the ruler and the picture of the microscope are not on the handout, but this picture is. And this picture is simulating what the ruler might look like for a specific microscope here. And so it's telling you here in the instructions here, you're looking under, this is a simulation, you're looking under scanning power, which is a total magnification of 40. And in practice, you always are going to draw, when you're in the lab, you would draw what you're looking at. You label what you're looking at. So in this case, we're looking at a metric ruler. Well, it's actually done for you here. And then you indicate what the magnification is. So what your total magnification is. And then down here, the idea is to estimate the size. In this case, we're estimating the size, the diameter of the field of view. And here, the size of the millimeter marks matters because you're under magnification. They're thick right now. And so the strategy I often tell students to do is to, once you start looking at the ruler and you focus in on it, move the first millimeter mark, move the ruler until the first millimeter mark moves right off of the edge of the field of view, so you can't see it anymore. You know it's there, and the edge is right there. And that makes the right side of the mark, there's a right side and a left side, makes the right side of the mark your reference point. So that would be considered 0. You can't see this right off of the field of view. And that means you have to go to the right side of the next one to get to another millimeter. So that's 1 millimeter. If you come to this side right here, that's not a millimeter because you haven't gone all the way to the right side yet. So that's not a millimeter. That's a millimeter. Then you have to go all the way to the next one to get to the next millimeter. So that's 2. This would be 3. And then it's not 4 because the 4th mark goes off of the field of view. So it is actually less. So you have to use your imagination, a little bit of estimation, where you think that other mark is outside of the field of view. And when you do, from here to here, this imaginary line out here is 4 millimeters, but we're not. We're somewhere between 3 and 4. And so the halfway mark is probably around here. So that would be 3.5 about. But the edge is right here. So that to me looks more like 3.7 or 3.8. I'm going to go ahead and call that 3.8. So that's 3.8 that you're right there, and the units would be millimeters. Okay, so once you know that, that's your field of view for scanning. The problem here is when you go to low power or you go to the high power, you're going to see less and less of that ruler. In fact, the millimeter marks get so thick and so big you can't even make an estimate at the next magnification. So now what do we do? Okay, so remember, as you go up in magnification, you see less and less of the field. The field gets smaller, right? So now it turns out there's a mathematical relationship between the two. So the first thing is first, you only measure the diameter of the scanning, okay? And so we determined that one to be, I think we wrote 3.8. And the top of the column says millimeters already. So you don't need to write it in the box because everything in that column is in millimeters. Okay, so it turns out there's a relationship. Milli is 1,000 times smaller than a meter, and then micro is 1,000 times smaller than that. So if I were to, thinking about it, milli means 1,000th of a meter, and a micro is 1,000 times smaller than that. So that actually makes a micro 1,000,000 times smaller than a meter. But the micro compared to a millimeter is 1,000 times smaller. And so that means a simple conversion to go from milli to micro, which is a much smaller unit, is to just multiply by 1,000 because micro is 1,000 times smaller. So 3.8 millimeters is exactly 3,800 micrometers. It's just a smaller unit. It's the same distance. Okay. So all you have to do is figure out millimeters, and then you can convert to micrometers by multiplying by 1,000. So that's something to remember. Now, this scanning lens is the only one you can measure in practice. So there's a little star there and a little note down here that says it's the only one you measure. The rest have to be calculated. And they're going to be calculated based on an equation that shows the inverse relationship. So the equation is written there on that document. I'm going to go ahead and write it here for you. And on the left side is for the scanning information. The scanning one is, remember, the only one you measure directly. Now, we know the magnification for it because it's already built into the microscope. The microscope's total magnification under scanning is the value of the objective times the value of the ocular lens, and that came out to a value of 40. And so we know the left side of the equation because you measure the field of view directly, came out to 3.8 with the ruler, and we know the magnification, it's built into the scope. On the other side is where you're going to put the other lenses, right? So we're going to generalize and say for the low power, the high power, and the oil, we're just going to call that X for X magnification. And so the right side is those other magnifications. So magnification X, low, high, oil, okay? And then the field of view for that. Now the field of view is something we don't know. We cannot measure it directly. We don't know it. But remember, the magnifications are built in. We already know them. This was the total magnification for low is 100, for high is 400, and for oil is 1,000. So we know those. The only one we don't know is the field of view at those magnifications. And this equation then is used to calculate for low, for high, and for oil. Now it's a lot simpler to actually move the equation around first and then use that manipulated equation to do the calculations quickly. So because we're looking for a field of view here, we're going to solve for field of view, and that means get rid of magnification under the other powers and move it to the other side. So for multiplying here, the opposite of multiplying is dividing. So we're going to divide both sides by the new magnification. for the X magnification, and that cancels it here. And that leaves me with a new equation that's solved for just the field of view that we're looking for. I'm going to go ahead and put that field of view on the left side and then move the other stuff to the other side. It's the same equation. So what this equation tells me is I'm going to take the magnification and the field of view for scanning, and I'm going to multiply those two. And I'm always going to do that. It's always going to be scanning on top here. And then I'm going to divide by the new magnifications. Okay. Now, because you're not using a different microscope, the top part of this equation never changes. So I recommend, so that you can do this very quickly, is go ahead and plug in the information for the scanning on the top, calculate the top part, and save that number. The answer you get from the top. When you save that number, all you have to do now is divide it, that number that you saved, divide it by the different magnifications, and you get your answers right away. So I'll just show that in practice what you would do. So your field of view for whatever magnification, basically you're going to take. Now remember, you actually have to measure the field of view. The magnification is built in to the scope. Okay, so the magnification for the scanning is 40, and the field of view that we measured is 3.8 millimeters. Now remember, if you use a different microscope, it's going to have a different field of view. Okay, so you've got to always make sure you measure that first for scanning only. And the bottom is the magnifications you're going to divide by. So what I would do in practice is go ahead and multiply the top to get that answer, and then you save it, and then you use it. So you can do this longhand on paper, with scratch paper. You can do this with your calculator, or if you're good at mental math. So this comes out to 152, and the units are going to be millimeters, because their units are right there. And then the bottom is just the magnifications that you're going to divide by. So let's say we're going to try to figure out the field of view, not just for anyone, but for low, okay, for this microscope. All I have to do now is put that number that we saved from the top, which is 152 millimeters, and we're going to divide by 100 because that's the new magnification there. And when you do that and you run it in the calculator, you get 1.52 millimeters. Okay. I'm going to go ahead and round to 2 sig figs because there was 2 significant figures to begin with. There's a review of significant figures in your lab manual and lab exercise 2 if you want to go and review that. I'm not going to grade on significant figures, but I'm going to say they are important. So just promote an awareness for that. And if I want to make that into micrometers, just multiply by 1,000. Now, if I'm going to do this and continue to do this, I can do this for field of view, for high powered, and then for low power. And all I'm going to do is I'm going to change the bottom. So I'm going to take the 152 and instead I would divide by 400, and then take the 152 and then divide by 1,000 for the next one. So doing this for the next one would be 152 millimeters for high powered, and I'm going to divide by 400 instead. And when I do that and I punch it in the calculator, I'm going to end up getting 0.38 millimeters. And so I'm going to put 0.38, and then that gives me 380 micrometers. And then we do the same thing for the field of view for oil. And again, it's 152 on the top. And then I'm going to divide by 1,000 this time, and I'm going to get 0.15 millimeters. And then that comes out to 150 micrometers. So now that I have this table, you built this table. You do it when you first start using your microscope. Now you have it and you can reference it for whatever size plate you're using, right? Like going back to that Apple analogy on the plates. If I'm using a very a high magnification, the plate is smaller. That means I need to use a smaller field of view diameter. So if you're looking at something under high powered, then in this microscope, then your diameter is 380 micrometers. That's what you would use in that size equation. If you're using low power, then you use 1500 micrometers, or if the object's relatively large, you can still use millimeters and use 1.5. You're just getting the answer in a different units, right? So here's your example, and here's that fit equation that we developed earlier using the plate analogy. Right? And remember, the top is the field of views that we figured out in this table. You would plug this in, and the one you use depends on what magnification you're under. So these are some simulation problems, and here's an example problem here. Okay, you remember you always start, if you're working in the lab, you would draw in your lab notebook or your lab journal. You would label what it is. In this case, they're telling us this is an unknown specimen, so we didn't even know what it is. It's just some unknown specimen. It has a description. It's a filament growth pattern, and so we might label it as unknown A or number 1 because we haven't identified it yet. And it tells us that we're looking at it under high power. So this is example 1. And we're looking at it under high power, so that means you would be a total magnification of 400 power. Now, I'm kind of guiding you here and telling you label the specimen and label this. But in reality, your notebook doesn't have these things drawn for you. You draw them yourself. And then the idea here is to estimate size. So now this filament goes off of the field of view, so it doesn't make sense to figure out what the length is, but maybe another size we can figure out is the width of this one. So that's where we would go there. So now remember, to estimate size, the equation is the field of view. And in this case, the field of view is under high power, according to this simulation problem. We're simulating that this is what the organism would look like under a high-powered magnification. And then we need the fit number. And so I find it pretty handy that if the organism is small enough, it's not very big, then you can estimate how many fit to the middle, halfway, and then multiply that by 2. And so right now, if visually, I'm looking at now where the halfway point is in the field of view. All I have to do is figure out how many, in my mind, imagine how many line up, just like we did with the picture, and figure out how many line up. And if I do that, it looks like I get a little more than 3. So it's about 3. So that would be 1, and then another one there. So it's 3, 3.2, 3.3s, 3. We'll go with 3, and 3 is halfway, so that means it's 6 all the way across. So my fit number is going to be 6. That goes on the bottom. Now, the diameter of my field of view I need, and that we figured out before we even started looking at the specimens. And since we're looking at this specimen under high power, and it's pretty small, I'm going to use micrometers instead of millimeters. So I'm going to use 380 in this one. So you plug in 380, and don't forget the units, micrometers. And then you plug that in, and then you just go ahead and divide. So when I do that, that's 380. We divide by 6, and that gives me 63.3333. I'm going to round to 2 figures, so that's 63, and the units are micrometers. And that's your estimate of size for that one. Now, I do have some other practice problems on the handout that do this, so I'm just going to give a couple of pointers for you. This one is, now this is practice problem 1. Make sure you label what it is based on the description. It's a seed. This one is under scanning, so it's not high powered. So this one is under a total magnification of 40, and we have the table. That's the one we measure directly. You can either use millimeters or micrometers here, because this one's pretty large. You can probably use millimeters in that one for your field of view. Now the idea here is to get an estimate of how many fit going all the way across. Now this one's pretty large, so instead of going halfway, we can go all the way across. I think it's going to be more than 1, but not more than 2. So you have to visually estimate 1, and then in your mind line up another one, and then see how much of that seed you think goes would cover the rest. It's going to be 1 point something probably. So work on that one and try to figure out what the answer is practice. And then practice problem number 2. This is bacteria, so you would label it bacteria, and this one is under oil, so your total magnification is 1,000. So on that one, you're gonna need to use what we figured out for the diameter of the field of view is for oil, which is 150 micrometers. Now these guys are pretty small, so I'm gonna give you a strategy for this one. When they're really tiny, it's even hard to estimate. It's hard enough when they're not that tiny to go all the way across, so I recommended you go halfway across. But here, I'm going to recommend that you divide half of this into 5 equal, and you're doing this in your mind, right? And if you do that, you're going to basically equally space 4 of them here, and that gives you 1, 2, 3, 4, 5 spaces, and then that means 5 more going this way. So what you've done is you've broken up visually into 1/10. And so what I would do is I would look at one of the cells that's about the average size there, and then in my mind I'm going to place it there, and then think in my mind, how many would it take to get to that first line? And if I do that, maybe it's 4, it's 5, it's 6, however many you think go to that first line. And if you do, that's how many fit 1/10 of the way. So that means you would need to take that number and multiply by 10 to get the total number. So if I think 7 fit that first line, I'm just throwing out a number. You practice trying to do that estimate. But let's say I think it's 7, then it would be 70 going all the way across. That's 70 because I'm figuring out how many fit 1/10 of the way. Okay? And then there's one more, which practice problem 3, which is an amoeba. So you label amoeba, and this one is under, it says high-powered, but then it says 100. So that's not high power. This should say low power. So we want to make sure we fix that. I'm going to try to fix that on the handout before you download it tonight, before you see it tomorrow or the next day. And so let me go ahead and fix that for you. And then there's the last one says make up your own problem. So make up something, make up some magnification, make up some object, draw it on the microscope, and then you've made up a problem, just like if you're doing your own practice problem. And then at the end here, you can always pause this for yourself and then try to do this. This is an example of how you might be assessed. It's a practice problem that's sort of like in the testing format. You would get a description. You're using a microscope. You can see this is a different microscope because this is what the router looks like under scanning, and it's a different diameter. So different microscopes are going to have different field of views, but you can only measure the scanning one. So here, this is what the microscope looks under scanning, and then they put a slide on there and they're viewing it under low power, right? So those equations we were using apply, but the diameters of the field of view are different now because this is a different microscope. So you have to go through all of those processes to be able to answer it. So here are the two sample questions that you might get. So you might want to see if you can try to answer those as you prepare for the types of questions you might get on an assessment. So I hope this helps. If you do have any questions, you work through this, let me know.